Today I want to start with an assumption that seems utterly obvious, an assumption that has accompanied modern science for centuries, to the point that we rarely stop to ask what it really means. I've thought a lot about our position in the universe, not just where we are, but where we are physically permitted to be, and that is far from intuitive, because in everyday life we're accustomed to thinking that every position is interchangeable. A table can be placed in any corner of a room. A person can stand here or there without changing the essential nature of the room. From that intuition, science formed a very powerful principle. We are not in a special position. Earth is not the center. The sun is just an ordinary star, and our galaxy is merely a tiny dot among hundreds of billions of galaxies. This principle, often associated with Copernicus from the 16th century, has worked extraordinarily well. Thanks to it, we have dared to extrapolate the laws of physics measured here on a small planet orbiting an unremarkable star to the entire universe. But then when you really pause and think more carefully, a slightly uncomfortable feeling begins to emerge. If our position is completely unprivileged, if we are just a random point in space and time, then why is it precisely at that point that the conditions exist, allowing stable atoms, stars to burn for billions of years, complex chemistry to form, and ultimately living beings capable of questioning the universe? This does not deny the Copernican principle, but it forces us to reconsider how we have been using it. Perhaps the issue is not whether the universe has a center, but rather that not every position permits the existence of observers. And that thought, though it sounds very simple at first, opens up a series of deeper questions about what we mean by not special, when the very existence of the observer is already a highly special condition. It is from there that another idea gradually took shape, not to reject the Copernican principle, but to supplement it with a condition we had previously tended to overlook. This idea was clearly stated for the first time in 1973 by Brandon Carter in a presentation at a symposium of the International Astronomical Union in Krakow. Carter pointed out a very simple fact, so simple it is easy to dismiss as trivial. Any observation of the universe must be made from a place and time that permits the observer to exist. If the physical conditions do not allow life, for example, if stars cannot exist stably for billions of years, if heavy elements like carbon or oxygen cannot form, then there would be no creature there to ask questions about the universe. From this realization, what is called the anthropic principle came into being. In its weakest form, Carter simply said that we are bound to observe the universe from an environment compatible with the existence of observers. This is not a metaphysical claim, and certainly not an assertion that the universe was designed for humans. It is purely a logical reminder that science must accept all observational data are influenced by who the observer is and where they are in space-time. When we look out at the universe and see that the physical constants lie within very narrow ranges that permit life to exist, that does not necessarily mean those values are universal. It only means that if they were not in that range, we would not be here to measure them. In statistics, this phenomenon is called selection bias or sampling bias, and in cosmology, it becomes especially subtle because we have exactly one universe to observe. The problem arises when this idea is taken too far. If used carelessly, the anthropic principle can be turned into an empty explanation. The universe has this feature because otherwise we would not exist. It sounds reasonable, but it provides no mechanism, makes no predictions, and does not help us understand the laws of physics more deeply. It merely reminds us of our observational position. And if we forget that limit, we very easily confuse explaining the universe with inadvertently justifying our own existence. As we delve deeper into the specific details of this picture, we begin to touch on a problem that has caused many physicists to think seriously for decades. The fundamental constants of nature and the initial conditions of the universe appear to lie within extremely narrow ranges of values. This is not a poetic observation, but a direct conclusion from physical calculations. For example, if the gravitational constant were only a few orders of magnitude larger or smaller, stars would burn too quickly in just a few million years, or never reach temperatures high enough for fusion reactions. In that case, heavy elements such as carbon, oxygen, or iron, synthesized in stellar cores and supernova explosions, would not exist. Similarly, if the fine structure constant alpha, 1/137th, changed by just a few percent, atomic structure would become unstable, making complex chemistry, the foundation of life, impossible to form. Another example often cited is the cosmological constant, measured in 1998 through observations of Type Ia supernova. If it were larger than its current value by roughly 10^7 in Planck units, the universe would expand too rapidly for galaxies to form. These numbers show that our universe appears to be perched on a fragile boundary between a richly structured world and a completely empty one. Faced with that reality, one proposed explanation is the idea of a multiverse, which emerged in many eternal inflation models from the 1980s, associated with physicists like Alan Guth and Andre Linde. If there exists a vast number of universes with different constants, then the fact that a very small fraction of them fall into the life-permitting range is no longer puzzling. We observe a universe like this simply because only in such universes are there observers to observe it. I do not regard the multiverse as the final answer to the fine-tuning problem, and it itself has no direct observational confirmation yet. But the emergence of these arguments reveals something more important. Perhaps the core question is not only why the constants of the universe have these values, but also whether the way we pose the question, from the position of an observer existing in a very special universe, is causing us to confuse understanding the laws of physics with inadvertently reflecting our own conditions of existence. When we place the Copernican principle next to the anthropic principle, a subtle tension begins to emerge, not as a noisy contradiction, but as a quiet, nagging discomfort in the way we think about the universe. The Copernican principle, originating from the astronomical revolution that began in 1543 with Nicolaus Copernicus's work, was gradually reinforced through the 19th and 20th centuries as astronomy showed that Earth is not at the center. The Sun is merely an ordinary G-type star, and our galaxy is just one among hundreds of billions in the observable universe. In its modern form, this principle is used as a probabilistic assumption. If you pick a random position in the universe, it is highly likely to be unremarkable compared to ours. That very assumption allows physicists to believe that the laws measured on Earth, from atomic spectra to field equations, also apply to light coming from galaxies billions of light years away. And observations throughout the 20th century have continually confirmed this. But in 1973, when Brandon Carter stated the anthropic principle at the International Astronomical Union Symposium, another layer of reasoning was put on the table. Carter emphasized that every observation is constrained by the existence conditions of the observer. We cannot randomly select just any point in space-time to observe, because the vast majority of such points do not permit life to exist even for a few seconds, let alone billions of years of biological evolution. In cosmology, where physical constants must lie within very narrow ranges for stars and complex chemistry to exist, this creates a severe selection bias. In other words, Copernicus advises us to consider ourselves typical, while the anthropic principle reminds us that we can only appear in circumstances that are highly atypical compared to the entire possible space of physical conditions. Each principle makes sense on its own, but when placed side by side, they pull our thinking in opposite directions. If we truly are not special, why does all the observational data come from an environment so rare that it permits life and consciousness to form? And if we are forced to observe from such rare environments, to what extent do those observations still represent the entire universe? I do not think this is a paradox that can be resolved with a new catchy slogan or a cleverly named principle. On the contrary, it is more like a methodological warning. The Copernican principle is a statement about our position in the universe in probabilistic terms, while the anthropic principle is a statement about the necessary conditions for there to be an observer. When we use one to undermine the other, the risk is that we slide into conclusions that sound profound but produce no testable predictions. Therefore, rather than rushing to reconcile these two principles, I want to keep that tension alive. It is precisely this tension that forces us to re-ask a seemingly obvious question. When we say we are observing the universe, which part of it are we actually observing? And from a position selected by what conditions? If you listen long enough to the way we talk about cosmic science, it is easy to develop an implicit feeling that if we go far enough, collect enough data, and write enough equations, we will eventually reach a completely objective viewpoint on the universe. This idea is never bluntly stated in a scientific paper, but it creeps into the language, the diagrams, and the models. When Albert Einstein constructed special relativity in 1905 and general relativity in 1915, his equations described space-time as an overall structure applicable to the entire universe. When Edwin Hubble announced in 1929 that galaxies are receding from us according to a linear law, the expansion diagrams of the universe looked as though they were drawn from a position outside, looking down on the entire inflating space-time. By the end of the 20th century, maps of the cosmic microwave background radiation from satellites COBE, WMAP, and later Planck showed the temperature of the early universe with precision to 1 part in 100,000, further reinforcing the sense that we hold a panoramic picture in our hands. I often call this feeling the God's eye view, not because science believes in God, but because it evokes the illusion that there could exist an imaginary vantage point from which the entire universe appears complete and unbiased, as if we had stepped outside the very system we are describing. The irony is that this illusion does not stem from poor science, but from the very success of science. When we say that the laws of physics are universal, that they apply from laboratories on Earth to galaxies billions of light years away, that statement is entirely correct within its scope. But with just a small slip in language, universal easily gets misinterpreted as visible from everywhere, and from there into the feeling that we are standing in a place that belongs nowhere. In reality, all the data used to draw those seemingly omniscient pictures come from a very specific position, a small planet orbiting an ordinary star at a very late moment in the history of a universe, about 13.8 billion years after the Big Bang. Mathematical language may obscure this, but it cannot erase the fact that every scientific statement is tied to an observational context. Who measures where with what instrument over what period of time? The fact that we are not at the center of the universe does not mean we are nowhere at all. We are always at a very specific position in space and time, and that position determines which signals can reach us, which phenomena remain forever beyond our observational horizon, and even which questions are meaningful to ask. There is no completely unbiased observational position, because the very concept of observation already implies an asymmetric relationship between the observer and the observed. This does not make science subjective in an arbitrary sense, but it sets a clear boundary on the ambition of omniscience. When we forget that boundary, we begin to speak of the universe as though we have stepped outside it, as though our models not only describe reality, but replace it. What I want to emphasize is not to diminish the power of science, but to place it in its proper context. Science is powerful not because it gives us a God's eye view, but because it gives us the best possible models from the position we are forced to occupy inside this universe. In everyday life, we often understand observation as a passive, almost cost-free action. Just open your eyes, and the world presents itself to you. But physics, especially 20th century physics, has forced us to abandon that naive understanding. As early as the late 19th century, James Clerk Maxwell showed that light is not an abstract thing, but an electromagnetic wave carrying energy. This means that even the simplest act of looking requires a physical exchange. Photons must leave the source, carrying energy E equals sign, and enter our eyes or measuring device. No photons, no signal, no observation. By 1900, Max Planck showed that energy is not transmitted continuously, but in discrete quanta, setting a fundamental limit. All information must be carried by finite packets of energy. This leads to an inescapable consequence. Any interaction sufficient to transmit information is also sufficient to change the observed system. When you measure the temperature of an object with a thermometer, the two systems must exchange heat until equilibrium is reached. That exchange, however small, still alters the object's initial state. When you determine the position of a particle, you must make it interact with light or some field, and that very interaction changes the particle's momentum. This was clearly quantified in 1927, when Werner Heisenberg stated the uncertainty principle. The uncertainty in position and momentum of a particle always satisfies the relation. This is not a limit of technology, but a structural limit of nature itself. Even in astronomy, where we imagine we are only passively looking, the reality is no different. When we observe a star 1,000 light years from Earth, that light has carried away a portion of the star's energy over a millennium-long journey. That portion of energy is negligible compared to the star's total radiated power, but it is not zero. The world does not provide information for free. Every bit of information has its physical price, and that price is always paid through change. What matters is not whether the change is large or small, but that it is never zero. When this argument is pushed to its limit, the ambition to observe the entire universe begins to reveal its structural problem. To observe everything, we would have to collect information from everywhere, at every scale and every moment. But to collect information on that scale, we would have to interact on that scale. Such a comprehensive interaction would not merely record the universe, it would become part of the universe's history, altering the very thing it seeks to describe. The universe, after such a total observation, would no longer be the pristine universe, but a universe that has been intervened in. This is not a paradox created by words, but a direct consequence of how information is transmitted in the physical world. This limit does not depend on how advanced our technology is in 2025 or 3025. It is not a problem waiting to be solved in the future, but an inherent feature of any meaningful measurement. When viewed this way, the inability to observe the entire universe is not a failure of science, but an inevitable consequence of science being based on observation, and observation is always interaction. What science can do is not to eliminate the influence of measurement, but to understand, model, and accept that influence as an inseparable part of the picture. It is from this acceptance that the boundary between what can be known and what cannot be known emerges honestly. Many people, upon hearing about the measurement problem in quantum mechanics, immediately think of vague things, human consciousness collapsing reality, or untestable metaphysical paradoxes. But if we go back to the historical and technical context where this problem emerged, the picture becomes far more down to earth. The measurement problem took clear shape between 1900 and 1930, when physicists like Max Planck Werner Heisenberg and Niels Bohr were forced to confront the reality that the familiar measurement concepts of classical physics no longer applied intact at the atomic scale. In classical physics, we can, at least in principle, measure the state of a system without significantly altering it. A planet orbiting the sun, millions of kilometers away, can be observed without affecting its orbit in any noticeable way. But at the microscopic scale, that no longer holds. To determine the position of an electron in a hydrogen atom, we must make it interact with a photon. That photon carries energy, E equals sign, and this collision inevitably changes the electron's momentum. The consequence of this was quantified by Heisenberg in 1927 with his famous uncertainty inequality, showing that no measurement can simultaneously give us absolutely precise position and momentum. The measurement problem, in this sense, is not the question, does reality exist when we're not looking, but a very concrete methodological question. How do we describe a system when the very process of gathering information about that system also participates in its dynamics? In the classic experiments of the 1920s, the measuring apparatus could no longer be regarded as a neutral entity standing outside. It became a physical system interacting directly with the object being measured. This led Bohr to the principle of complementarity, which emphasized that there is no natural sharp boundary between the observed system and the measuring apparatus. This division is largely a pragmatic convention. A quantum state, therefore, is not a list of independent properties existing out there, but a mathematical tool that allows us to predict the probabilities of specific measurement outcomes under defined conditions. Understood this way, the collapse of the wave function is not a mysterious physical event occurring in space-time, but an update of information when a measurement is performed. At its core, quantum mechanics does not say that reality depends on consciousness. It says that every physical description is tied to a measurement context. Connecting this to the ambition of observing the entire universe, the lesson becomes very clear. If even at the atomic scale, we cannot completely separate the observed system from the process of observation, then the idea of treating the universe as an object out there to be fully observed becomes even less tenable. The universe is not sitting on our laboratory table. We are inside it. The measurement problem, therefore, is not an invitation to metaphysics, but a very sober methodological reminder. The task of physics is not to describe reality from the outside, but to build consistent models that connect measurements, measuring devices, and observational results. Acknowledging this does not weaken science. It makes it more honest about how knowledge is actually produced. In science, we often speak of data as if it is lying out there, ready to be collected, as though the universe contains complete answers, and our job is merely to ask the right questions. But as early as the mid-25th century, physics and information theory forced us to abandon that way of thinking. In 1948, Claude Shannon published the foundational work on information theory, in which he showed that every information channel has finite capacity and is always accompanied by noise. This has a very clear consequence. Information is never free. Every bit of data we obtain comes at the cost of specific trade-offs in measurement. In quantum mechanics, this was already quantified very early. In 1927, Werner Heisenberg pointed out that if we want to determine a particle's position with greater precision, its momentum uncertainty must increase accordingly. This is not a limit of crude instruments, but a structural limit of measurement itself. Similar trade-offs appear at every scale. In astronomy, to detect an extremely weak signal from galaxies billions of light years away, telescopes like Hubble or James Webb must accumulate photons over many hours, even days. In return, they lose the ability to track rapid variations occurring in seconds or minutes. Conversely, fast sky survey telescopes must accept lower spatial resolution. To cover a wide swath of sky, we sacrifice detail. To gain detail, we must narrow the field of view. These trade-offs do not disappear as technology advances. They only change form. We can reduce noise, but we cannot make noise zero. We can optimize experimental design to measure one particular quantity with very high precision, but the price is that other quantities become less well defined or are completely ignored. Every measurement is a deliberate choice, choosing what is important in the current context and accepting that everything else will be blurred or submerged in noise. When our ambitions extend to questions about the entire universe, the price of information becomes a central issue. To describe the universe on large scales, we must accept that countless microscopic details are averaged out. To study microscopic processes, we must give up the panoramic view. There is no measurement setup that allows us to retain everything at once. The idea of a perfect measurement, one that records every aspect of a system without introducing noise, without trading precision for scope, without sacrificing scope for resolution, is simply incompatible with the way information is transmitted in the physical world. Every information channel is limited by the energy required for interaction, by irreducible background noise, and by the constraints of space-time. When we try to overcome one limit, we usually bump into another. This does not devalue science. On the contrary, it explains why science must advance selectively. We never read the universe passively. We pose specific questions and receive answers shaped by the very way we ask them. Viewed this way, the ambition to observe the entire universe reveals a deeper problem. It demands a measurement that pays no price, while the very structure of measurement is bound up with trade-offs. Rather than seeing this as a failure, I consider it an important pointer. Science does not progress by collecting every imaginable piece of information, but by selecting the information most meaningful for the question at hand. There is no perfect measurement, but there are measurements that are good enough in specific contexts, and it is precisely the acknowledgement of the price of information that keeps science honest with the world it is trying to understand. The trade-offs in measurement show that information never reaches us in full. But even before we talk about instruments or methods, the universe itself imposes a far stricter limit on our access to information. That limit arises directly from the structure of space-time, first consistently described in Albert Einstein's special relativity of 1905. In this framework, the speed of light in vacuum, CO 299,792 kilometers per s, is not a technical detail, but the maximum speed at which any signal or causal influence can propagate. This means that every piece of information that wants to reach us is bound by an absolute time limit. The consequence of this limit becomes clear in modern cosmology. From measurements of the cosmic microwave background radiation by satellites COBE, WMAP, and Planck, we know the universe is about 13.8 billion years old. Because light can only travel at a finite speed from any position in the universe, only regions within the distance that light has had time to travel in 13.8 billion years can send information there. This limit is called the observable horizon, and its current radius is about 46 billion light years due to the expansion of space. What is important is that this horizon is not a material wall or a boundary where the universe ends. It is an information boundary, the line between what can causally affect us and what is forever beyond reach. Light from regions beyond this horizon will never reach Earth, not because it is too weak or because our telescopes are not strong enough, but because the space between us and those regions is expanding at a rate that makes the distance grow faster than any signal can travel. According to the standardized LTCDM models from the late 1990s onward, many galaxies are now receding from us at effective speeds greater than c, which does not violate relativity because space itself is expanding. From our position, we are confined within an observational bubble determined entirely by the geometry of space-time. The key point is that this limit does not apply only to humans or to Earth. It applies to every imaginable position in the universe. Whether a civilization exists in the Andromeda galaxy or at the farthest edge of the observable universe, they too will have their own horizon, with regions forever unable to send information to them. There is no privileged vantage point from which the entire universe can be seen at once. Every point in space-time is surrounded by inescapable causal boundaries. When we speak of the entire universe, it is easy to forget that the concept far exceeds what can be observed from any single viewpoint. Much of the universe, if it exists beyond our horizon, leaves no direct trace in the data we collect. We can infer about it through theory. We can build models of the overall structure of space-time, but those inferences do not have the same epistemic status as direct observation. When combined with the unavoidable trade-offs in measurement, the picture becomes clear even in the most ideal scenario. With perfect technology and zero noise, we would still be stopped by the information boundary of the universe. Space-time is not merely the stage on which matter and energy move. It is an active barrier that determines what can be known by whom and when. Therefore, the idea of observing the entire universe encounters not only experimental or methodological difficulties, but also a non-negotiable geometric limit. Acknowledging this does not make the universe more mysterious. It makes the picture more honest. What we know is always what can be known from the inside, under very specific constraints imposed by the structure of space-time itself. The information boundaries erected by space-time are not yet the final filter between us and the universe, because even signals within reach of the observable horizon must pass through another filter, silent but absolute time. When we say we are observing the universe, it always means we are looking into the past. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. Light from the nearest star outside the solar system, Proxima Centauri, takes about 4.24 years. And light from galaxies at the edge of the observable universe, recorded by the Hubble Ultra-Deep Field, left its source 10 to more than 13 billion years ago. No measurement allows us to see the universe as it is happening in an absolute simultaneous sense. What we call the present of the universe is always a composite picture stitched from countless pieces of the past, each carrying a different delay. This is not a technical limitation that can be overcome with better equipment, but a direct consequence of the space-time structure described in Albert Einstein's relativity, 1905-1915. In relativity, there is no universal now that applies to the entire universe. Events are ordered according to time slices that depend on the observer's state of motion, and two events simultaneous in one reference frame may not be simultaneous in another. This is not a complicated mathematical detail reserved for physicists. It is a physical statement about the world. Time does not provide us with a neutral plane on which to gather all events at once. When we observe the night sky, we are not only looking across spatial distances, we are looking across multiple layers of time. A galaxy may appear stable and peaceful in today's photograph, while in reality it underwent a violent collision hundreds of millions of years ago. The light carrying that information simply hasn't reached us yet. Therefore, even within the region of the universe, fully inside the observable horizon, the picture we obtain is temporally out of phase. There is no way to synchronize all signals, no way to wait until the entire universe updates to a common moment. Time, in this sense, is not just an axis for marking events. It is a mandatory perceptual filter. It determines the order in which information reaches us, shapes the causal relationships we can infer, and even the stories we can tell about the history of the universe. When cosmologists reconstruct the 13.8-billion-year history of the universe, from Kolb 1989, WMAP 2001, and Planck 2009 cosmic microwave background data, they do not observe that history as a sequence of ongoing events. They piece it together from traces arriving from different times, through models and inference. This makes the ambition to observe the entire universe even more fragile. Even if, in imagination, we could overcome every limit of energy, noise, and spatial extent, we would still be blocked by time. To observe the entire universe at a single instant, we would need an information access that suffers no delay, unbound by the causal structure of space-time. But no such access exists in the physics we know. Time is not a curtain that can be pulled aside. It is part of the structure of reality itself. Every measurement occurs in time, and every piece of information carries its timestamp. When we say we understand the universe, it means we understand a network of relations filtered through time, not a snapshot of all of reality. This realization does not devalue our knowledge, but places it in its proper position. We are not spectators watching a live broadcast of the universe, but people trying to piece together the story from frames that arrive late, early, and never perfectly synchronized. And precisely because time is an unavoidable filter, every ambition to grasp the entire universe in a single glance runs into a fundamental truth. The universe always reaches us through slices of the past, and there is no physical path that allows gathering all those slices into a total present for observation. When we put all these pieces together, the unavoidable interaction of measurement quantified by Werner Heisenberg in 1927 with the uncertainty inequality, the price of information systematized by Claude Shannon in 1948, the space-time boundary set by the speed of light CR, 299,792 kilometers per s in Albert Einstein's relativity, along with the time filter that makes every observation a look into the past, a conclusion begins to emerge, but it is not an answer so much as a correction of the question. The problem with the phrase, observing the entire universe, is not that it is too ambitious, but that it is misstructured from the start. It assumes the existence of a state of the universe that can be observed as a complete object and a position, physical or conceptual, from which that observation can take place. Whereas in reality, with a universe 13.8 billion years old and an observable horizon radius of about 46 billion light years, no information access is unbound by interaction, by causal boundaries, and by time. Posing the question that way is to ask science to do what the very conditions of science do not permit. A classic analogy that clarifies this structural impossibility is Kurt Gödel's incompleteness theorems of 1931, which show that a sufficiently powerful system cannot be both complete and self-proving consistent from within. Similarly, a map attempting to measure itself falls into an infinite loop, not because the map is poor, but because the requirement is impossible. When we demand to observe the entire universe, we are asking a system inside the universe to describe the universe as a whole, including itself without leaving any trace of the describing process. And this logical loop cannot be broken by more data or better instruments, because it is a structural problem, not one of resolution or scope. In its best practice, science has never promised that since the LFTTM model was standardized in the late 1990s based on type Ia supernovae and cosmic microwave background, cosmology operates by connecting observations that can be made in defined contexts and tested through predictions. When we slip into the language of the whole and the absolute, we step outside the territory for which the scientific method was designed. This does not make big questions meaningless. It forces us to reframe them correctly. Instead of asking whether the entire universe can be observed, a more scientific question is what we can infer about the structure and history of the universe from this position, under these constraints. Instead of seeking a complete picture, we build models that consistently connect discrete pieces of data, accepting that every model has a domain of applicability. The map analogy is not meant to diminish models, but to emphasize that the best map is not the biggest map, but the one best suited to the purpose. A city map does not need every grain of sand to give directions, just as a cosmological theory does not need every microscopic detail to explain expansion. And the problem only arises when we demand the map to become the territory. Reframing the question is not evasion, but methodological maturity. Many of the greatest advances in physics have come from realizing that the old question was wrongly posed rather than from finding new answers to it. And when we accept that observing the entire universe exceeds the structure of measurement and information, we free ourselves from an impossible goal to focus on more realistic ones, understanding the laws governing what can be observed, discovering verifiable connections, and building models strong enough to be challenged, and when necessary, refuted. When science has learned to say impossible in a serious way, an interesting paradox emerges in the modern context. We have never had so much data as we do now, and the illusion of knowing everything has never been so seductive. In 2020 alone, the world generated about 64 zettabytes of data, and that figure is projected to exceed 180 zettabytes by 2025, according to industry reports. The accelerating pace of collection and storage creates the feeling that if we just have enough data, every limit will eventually be worn down. But this sense of omniscience comes mostly from the sheer abundance of numbers, not from an understanding of the structure of information. Data does not speak for its own meaning. It is always collected according to defined criteria, from instruments placed at defined positions, over defined periods of time. Every data set reflects prior choices, whether we are conscious of them or not. As the scale of data grows, biases do not disappear. They get amplified. The idea that enough data will automatically neutralize bias is a dangerous misconception, because more data does not mean unbiased data. At the same time, the rise of AI makes this illusion even more convincing. Machine learning models process enormous volumes of information, uncover subtle patterns, and achieve impressive accuracy in specific domains. But methodological rigor is easily obscured by pragmatic success. An AI model, no matter how large, remains a model trained on available data, with defined objectives in a finite problem space. It does not transcend the information boundaries imposed by space-time, does not erase the time delays of observation, and does not exempt itself from the cost of measurement. When the model performs well, it shows that it efficiently exploits structure in the provided data, not that it has achieved an unbiased view of all of reality. The risk arises when we shift from local success to implicit claims of comprehensiveness, talking about the model of everything, about the ability to simulate all of reality, while forgetting that every simulation requires input data. Every piece of data has already been filtered, and every model has a domain of applicability. Methodological boundaries do not vanish when algorithms become more sophisticated. On the contrary, they need to be emphasized more, because complexity obscures hidden assumptions. This was warned about early in modern data science and machine learning, where studies on data bias and out-of-distribution generalization from the 2010s onward showed that large models often interpolate very well within familiar domains, but fail when extrapolating beyond them. Applied to the cosmic story, the conclusion becomes even clearer. No amount of data can cross the information horizon. No algorithm can erase time delays, and no model can turn itself into an external vantage point. Big data and AI are powerful tools. Their strength lies in better exploiting what can be observed, not in erasing what cannot. Emphasizing methodological boundaries is not conservative. It is the only way to use the power of modern tools correctly, without fostering the illusion that every limit is merely a technical problem. The illusion of knowing everything often leads directly to another subtle confusion, conflating the tool with the reality the tool is describing. In science, our most powerful tool is not the telescope or the particle accelerator, but the model. From the time Isaac Newton published the Principia in 1687 to when Albert Einstein completed general relativity in 1915, physics advanced by drawing maps of reality, using equations and mathematical structures. And for most of that time, these maps worked extraordinarily well. Planetary orbits were predicted with errors smaller than 1 part per million. Gravitational waves were detected in 2015, exactly as predicted a century earlier. Precisely because of that success, it is very easy to forget a fundamental truth. The map is never the territory. A city map at 1/10,000 scale helps you find your way, but it omits every brick and every crack. That simplification does not make the map wrong. It makes it useful. In physics, equations are the same. They retain the quantities directly relevant to the question at hand and discard the rest. When the question changes, the model must change accordingly. Confusing the equation with the universe leads to the expectation that if we just find the right equation, everything will automatically be explained. But even the most successful theories have clear domains of applicability. Newton's classical mechanics describes macroscopic motion well at speeds much less than c raw, 3k 10^10 kenneth, but fails at atomic scales. Quantum mechanics, formed between 1925 and 1927 with Heisenberg and Schrödinger, describes the microscopic world well, but says nothing about gravity on cosmic scales. General relativity describes space-time structure very accurately on large scales, but has not yet been reconciled with quantum mechanics. Each model is a compromise between precision and tractability, between generality and specificity. When we forget this, the model begins to be treated as a complete portrait of reality, and anything outside its scope is seen as a bug to be fixed, rather than a sign that we are asking a different question. In modern cosmology, models like LFA-CDM allow us to infer the history of expansion and matter distribution from cosmic microwave background data, but they do not turn inference into direct observation, nor do they erase the information boundaries set by space-time and time. Talking about the entire universe in a model only means the most comprehensive ambition within what can be tested, not that we have accessed the universe as a fully observable object. Recognizing the role and limits of models does not weaken science. It helps us use models in the right place, ready to revise or replace them when new data appear, and avoids the temptation to equate predictive success with absolute understanding. Science advances not because we have ever more perfect maps, but because we get better at knowing what our maps are for and when we need to draw a different one. And if we cannot observe the entire universe, if every model has limits, then what do we actually know? This is not a skeptical question in the sense of denying knowledge, but a question about the legitimate boundaries of knowing in science. In modern scientific practice, knowing does not mean possessing a complete picture of reality, but having statements tightly linked to performable measurements, testable predictions, and clearly stated conditions of applicability. We know the laws governing planetary motion, because from Johannes Kepler in 1609, 1619, to Isaac Newton in 1687, orbits were measured, predicted, and verified with ever-increasing precision. Today, radar and laser measurements allow orbital dynamics to be tested with errors smaller than Hentheiner's quarters in space navigation problems. We know the universe is expanding because since Edwin Hubble's 1929 discovery of the redshift distance relation, galaxy surveys, and especially Type Ia supernovae in 1998, have reinforced the quantitative link between distance and recession velocity. Cosmic microwave background measurements by COBE, WMAP, and Planck allow us to determine the universe's age at about 13.8 billion years with percent-level uncertainty. In these cases, knowledge is not an absolute claim, but a network of connections reinforced through repeated testing. The core is that what we know is always tied to the specific questions we can pose to nature, and the answers nature can provide through observation. When a theory allows the prediction of new phenomena, and those predictions are confirmed, the scope of knowledge expands, but always with assumptions about the domain of applicability. Outside that domain, the theory may be silent or incorrect. What lies beyond observational capability is not automatically meaningless, but it does not have the same epistemic status as what can be tested. When talking about regions beyond the observable horizon of radius, approximately 46 billion light years, or epochs that leave no direct observational trace, we are talking about possibilities suggested by theory, not facts that have been observed. This distinction is very important, even though it is often blurred in popular discourse. Science does not forbid thinking beyond observation, but it demands a clear separation between what is inferred and what is measured. When this boundary is erased, it is easy to slide from science into storytelling. Recognizing limits allows us to assess the true strength of knowledge. We do not know every detail, but we know enough to build models capable of prediction and explanation over wide domains. We do not know every place and every time, but we know general laws stable enough to apply to very different phenomena. At the same time, we know that there are questions, however appealing, that currently lie beyond the reach of direct observation. Knowing this does not shrink knowledge. It clarifies its structure, helps avoid attributing to science claims it cannot defend, and prevents underestimating the achievements already made. Therefore, the honest answer to what do we actually know is we know what is tied to observation, verified by prediction, and placed within models with clear boundaries. The rest is not forbidden, but it demands caution, because there we are extending the map rather than stepping directly into the territory. In science, limits rarely act as walls blocking the path. They are more like contours that force us to think more creatively about how to proceed. When we acknowledge that we cannot observe the entire universe, a direct consequence of the speed of light, COR, 299,792 kilometers per s, established in Albert Einstein's relativity, we are forced to ask smarter questions about the part of the universe accessible within the observable horizon of radius, about 46 billion light years. When we know that every measurement comes with noise and trade-offs, clearly quantified by Werner Heisenberg's uncertainty inequality in 1927, scientists do not abandon measurement. They design experiments to maximize the information most relevant to the question at hand. It is precisely these constraints that create intellectual pressure, and history shows that pressure often gives birth to new ideas. When simultaneous measurement of all microscopic quantities became impossible, physics developed quantum mechanics to describe probabilities and correlations. when astronomers realize they only see the universe through light from the past, from 8 minutes for the sun to billions of years for distant galaxies, they turn that limitation into a tool using redshift distance relations and cosmic microwave background to reconstruct the 13.8 billion year history of the universe. Limits in this way do not merely constrain but also direct. They help distinguish between questions that can generate knowledge and questions that are merely verbally appealing. When we know there is no total present of the universe, a consequence of the relativity of simultaneity, we stop searching for a complete snapshot and focus on invariance and laws testable across different time slices. When we know models cannot be identified with reality, we evaluate models by their predictive power and their capacity to fail, rather than by their level of ambition. Science advances because of constraints, because constraints force us to choose without limits. Every direction seems feasible, and none gets pursued deeply enough. With limits, we decide what is important, what can be tested, and what should be set aside, at least for now. Those decisions do not impoverish science. They sharpen it, creating specific research programs, sophisticated experiments, and theories clear enough to be refuted. There is a beautiful paradox here. The more clearly we understand what cannot be done, the better we become at doing what can be done. Knowing that we cannot observe the entire universe does not prevent us from building an ever deeper picture of its structure and history. On the contrary, it reminds us that the picture is always assembled from real pieces, and its value lies in the strength of the connections, not in covering every gap. Limits also play an important psychological role. When openly acknowledged, they become part of the method, helping science avoid the temptation of false omniscience and creating an environment where new ideas can be seriously tested without pretending to solve everything. Science, in this sense, is not a race to eliminate constraints, but a process of learning to exploit constraints intelligently. When we view science through the lens of the limits and constraints discussed, a different picture gradually emerges, less glamorous but far more honest. Science is not a road leading to an endpoint where every question is answered, but an open journey where each good answer generates better questions. At its core, science is not a collection of immutable truths, but a continuous process of error correction. From the time Francis Bacon laid the foundations for the experimental method in the early 17th century, science has operated in a cycle. Propose hypotheses, build models, test with observation and experiment, then adjust or abandon when data do not support. This mechanism is not a sign of weakness. It is the greatest source of science's strength. A theory is not judged by its longevity, but by the number and severity of challenges it withstands. When new observations appear, like Edwin Hubble's 1929 redshift distance relation, or cosmic microwave background measurements by Kobe, WMAP and Planck, a good theory is not one that patches every discrepancy, but one that clearly recognizes when it is no longer sufficient. It is thanks to this error correction mechanism that science advances, not in a perfect straight line, but through increasingly refined adjustments. This also explains why the idea of a final theory, a closed set of equations explaining everything, sounds appealing, but is incompatible with the way science actually works. Even the most comprehensive theories are built on specific assumptions and tested in finite domains. They always leave questions at the edges. The history of physics shows this very clearly. Newton's mechanics becomes a limiting case of relativity as speeds approach Sears, 299,792 kilometers per s, and of quantum mechanics as scales go down to the microscopic. That does not make the old theories useless. It places them in their proper position. The absence of a final theory is not a tragedy, but a natural consequence of science always remaining open to new data and new ways of asking questions. From here, the value of intellectual humility becomes clear. not paralyzing doubt, but a sharp distinction between what we know very securely and what is merely suggested. Humility allows us to say, I don't know, without seeing it as failure, and I could be wrong without seeing it as weakness. Scientific confidence comes from knowing that if wrong, the method will detect it. This is especially important in cosmology, where powerful models like LECDM, standardized from the late 1990s, are built from finite sets of observations, filtered through time, space, and measurement methods. They can be extended, revised, or replaced as new data appear. Science as an open journey means there is no sign saying fully understood, only milestones sufficient to keep going. Each identified limit is not an endpoint, but a signpost, pointing where more caution is needed and where bolder questions can be asked. Viewed this way, the inability to observe the entire universe is no longer a regrettable deficiency, but a natural part of an always incomplete process of understanding. We do not stand outside looking at a closed hole, but inside, learning to read the traces the universe leaves, knowing that the picture will never be complete, but that each correctly placed piece makes the whole clearer. When I say there is no God's eye view, I don't say it with bitterness, and certainly not to lead to a nihilistic conclusion about knowledge or meaning. On the contrary, this is a liberating affirmation. If we look at it the right way, reality, as the results of 20th century relativity and information theory show, does not permit any system inside it to step outside and observe the whole from an absolutely neutral position. The speed of light, CR at 299,792 kilometers per s, sets a causal limit. The age of the universe, approximately 8 billion years, sets a temporal limit. And every measurement carries interaction and noise. These are not human deficiencies, but direct consequences of the fact that we are part of the world. We are trying to understand space-time. Information, causality, and observation are woven into the same structure, as has been clarified from Albert Einstein's work in the early 20th century to modern measurement standards. That structure has no room for an external platform. Every observation takes place from somewhere, at some time, with specific instruments and limits. When we abandon the illusion of omniscience, what is lost is not meaning, but an unrealistic expectation. In return, we gain a more honest understanding of our position. Accepting that we are inside does not mean arbitrary subjectivity. Science still achieves intersubjective objectivity, models that can be tested, replicated, and improved by independent groups, as the way cosmic microwave background measurements converge on the same cosmological parameters demonstrates. What we give up is only the idea of a viewpoint, without traces of position. When reality does not allow observation from the outside, knowledge must arise from the inside, and that imposes a clear requirement: state assumptions, specify context, accept domains of applicability. This is not extreme relativism. Some models are better than others by criteria of prediction and falsifiability. But all such distinctions are made from inside the system, not from a transcendent position. Accepting this position also changes the way we talk about the universe. Instead of a complete object waiting to be described, the universe is a system in which description is itself a physical process. There is no final story told from on high. Instead, there are local stories connected by theory and verification, always open to revision. This does not create emptiness, but the meaning of participation. We are not spectators, but participants, affected by the universe and trying to understand it. When we no longer try to stand outside looking in, we focus on deeply understanding the relationships we actually belong to. And paradoxically, it is precisely this abandonment of omniscience that opens up a more solid form of objectivity. Objectivity as the ability to compare, contrast, and synthesize multiple internal viewpoints within a consistent framework. The absence of a God's eye view is not a loss but a necessary adjustment of expectations, helping us stop searching for a non-existent vantage point and invest our intellect in what can be understood from the position we actually occupy. We are not at the center, and we are not omniscient. That has been decisively affirmed since Nicholas Copernicus published the Revolutionibus Orbium Coelestium in 1543, pushing Earth out of the central position and reinforced over centuries of observation, showing that the Sun is merely an ordinary G-type star among roughly 400 billion stars in the Milky Way. And the Milky Way itself is just an average spiral galaxy among hundreds of billions in the observable universe. No cosmic privilege grants humans the ability to see everything at once or understand everything completely, especially in a universe about 13.8 billion years old, divided by an observable horizon set by the speed of light, cr 299,792 kilometers per s. But that does not mean we are powerless. What is remarkable is that from a small planet orbiting an ordinary star, humans have still inferred universal laws. Isaac Newton's laws of motion and gravity apply to both the moon's orbit and the motion of binary stars. Thousands of light years away, stellar evolution theory, developed strongly in the 20th century, describes stellar life cycles from a few million to tens of billions of years, and the expansion history of space-time has been confirmed from Edwin Hubble's 1929 redshift observations to cosmic microwave background measurements by Cove, W.M. Appé, and Planck. This capability does not come from standing outside the system, but from finding stable structures inside it through comparison, repetition, prediction, and correction. Humans, in that sense, are more like learners than judges. Science does not demand knowing everything but provides a method to distinguish correct understanding from incorrect refined over centuries. Not being at the center also carries another important meaning. What we learn is not only about us. When physical laws are tested and confirmed in many contexts, from Earth laboratories to gravitational signals from black hole mergers detected by LIGO in 2015, they show that the universe has universal properties despite the local viewpoint of the observer. This is not a return to the illusion of omniscience, but the result of many limited viewpoints converging on the same common structure, the foundation of scientific objectivity. The limits we have discussed do not deny the ability to understand laws. They only prevent the ambition to understand every detail. We can grasp how processes work without knowing the state of every particle, understand the history of the universe without observing every moment. Our true position lies in between, neither helpless outsiders nor omniscient narrators, but capable learners within a vastly larger system. It is precisely the clarity about that position, not central, not omniscient, but capable of recognizing laws, that forms the most solid foundation for all our efforts to understand the universe of which we are a part. If we could observe the entire universe, if every question could be answered completely from an omniscient viewpoint, then science, in the sense we have practiced it since at least the 17th century, would cease to exist. It would become a complete catalog where everything is already listed, with no room for error, surprise, or discovery. But history shows the opposite is true. It is precisely because there is no final answer that science remains alive. From the time Galileo Galilei used a telescope in 1609 to observe Jupiter's moons, a crude instrument with magnification of only about 20-30 times, to when gravitational wave detectors like LIGO detected signals from black hole mergers in 2015. Science has advanced not by erasing limits, but by working within them. Each limit forces us to think more carefully about the questions we ask, refine methods, recheck assumptions, and accept that current understanding can always be expanded or revised. Those very limits create intellectual tension, and the history of physics shows that tension fosters creativity. Werner Heisenberg's 1927 uncertainty inequality did not kill measurement, but opened up quantum mechanics. The fact that we can only observe the universe through light from the past, from 8 minutes for the sun to more than 13 billion years for cosmic microwave background, did not deadlock astronomy, but turned time into a tool for reconstructing cosmic history. When we know we cannot know everything, we begin to care more about knowing correctly the things that matter. We learn to distinguish between what needs to be understood to move forward and what can be left open for now. This reflects a deep human value. Humans always live within limits of time, perception, position, and if everything were infinite, experience would lose structure. There would be no waiting, learning, or growth. Science in that sense is a refined reflection of how humans find meaning. It does not promise omniscience, but promises a path where every step can be tested, corrected, and improved. The absence of a final answer is not a gap to be filled, but a necessary condition for science to keep moving. Every time a theory explains a great deal, like Newton's mechanics or relativity, it simultaneously opens new questions at its edges. Those questions do not show failure, but show that the theory has gone far enough to touch uncharted regions. If the universe were simple enough to be fully captured in a final framework, science would have ended long ago. But with a 13.8 billion year old universe, expanding according to verifiable laws, and regions still beyond the observable horizon, science remains an unending dialogue between the known and the unknown. When placed alongside human values, the parallel becomes clear. We do not judge people by whether they know everything, but by how they learn and respond to their limits. Science is the same. It is strongest when it knows what it cannot do, so it can focus all its energy on what it can do well. Limits keep science honest, avoid empty promises, and maintain a healthy connection to reality. Saying we cannot observe the entire universe does not make the universe less interesting. It makes every piece of information more precious. Every measurement, every observation, every successful model, from determining the Hubble constant to measuring the fluctuations in the cosmic microwave background, is the result of careful work within very specific constraints. It is that finitude that creates value. Without limits, science would drift into untestable claims and lose its reason for being. With limits, science becomes a deeply human endeavor, imperfect, always incomplete, but continuously progressing. And because there is no final answer, each generation is invited to join this dialogue, asking new questions, using new tools, and seeing the world in new ways. At this point, I see no tragedy but an invitation. Limits call us to keep thinking, keep exploring, and keep living with incompleteness without losing curiosity. That is why, for me, limits are not something regrettable in science, but what makes science vibrant, meaningful, and deeply connected to the most fundamental human values. If there is anything I hope you take away after all these arguments, it is not a closed answer, but a mode of thinking, firmly anchored in reality. We have talked a great deal about what cannot be done. We cannot observe the entire universe because the information horizon is limited by the speed of light. See what? 3 quarts 10 station s. We cannot stand outside looking in because every observation occurs inside space-time. We cannot completely eliminate the bias of position and time. When light from the sun takes about 8 minutes to reach Earth and light from the cosmic microwave background, measured by satellites like COPE, WMAP, or Planck, has traveled nearly 13.8 billion years. But what matters is this: all these cannots do not lead to deadlock. On the contrary, they outline the true shape of the scientific journey, a journey not toward omniscience, but toward ever better understanding from the inside. Science has never promised a godlike viewpoint. From Galileo Galilei observing the sky in 1609 with a crude telescope to Albert Einstein constructing relativity in 1905, 1915, the strength of science has always lain in knowing where it stands. So, I want to invite you to continue thinking this way as an intellectual habit. Whenever you hear a grand claim that science is about to explain everything, ask yourself, from where is that observation made? Under what conditions? With what assumptions about measurement, data, and models? Not to reject science, but to understand it more deeply and honestly. We do not stand outside the universe. There is no metaphysical balcony from which to look down on all of reality. We are inside, governed by the very laws we are trying to discover. But that does not make us blind. From the inside, we can still recognize structure, detect laws, build models capable of prediction and testing. From Isaac Newton's law of gravity in 1687 to the detection of gravitational waves in 2015. Understanding the universe does not require escaping it. It requires learning to listen to what the universe can tell us through real information channels. This journey never ends, because every good answer opens new questions, and that is not a flaw, but the rhythm of knowledge. If one day we believed we had fully understood the universe, that would be the day science stopped breathing. But more than 4 centuries of modern science show that has never happened. Not because the universe deliberately hides, but because the nature of understanding, when done from the inside, is always an open process. We advance by connecting pieces of understanding, knowing the picture will never be complete, but that each correctly placed piece makes the whole clearer. I see in this not a loss, but a long-standing invitation to human curiosity. Science does not promise absolute certainty. It promises a method to continuously improve how we understand the world. There is a very real beauty in knowing we do not have a God's eye view yet, can still say something true about the universe. A beauty that lies in the balance between humility and ambition. When you look up at the night sky, you do not see the entire universe, and you never will. But what you do see, those points of light, thousands or millions of light years away, is enough to tell a profound story about where we live. Not the final story, but the current story, told from the current position, with current tools. Tomorrow, with new data and new questions, that story will be retold differently, not denying the old, but expanding it. The inability to observe the entire universe does not make this journey less meaningful. It makes the journey more real. We are not standing outside judging a finished play. We are on stage, both participating and trying to understand the ongoing performance. And it is in that role not omniscient, not central, but always learning, that humans find their true place in the universe, in a journey with no final curtain, only next steps, next questions, and ever opening new ways of seeing. If you find these questions worth continuing to think about, please subscribe to the channel so we can dive deeper together into how we understand the universe from our own position inside it. See you in the next part of the journey, where we will keep asking the right questions, even knowing the final answers will always lie ahead.